Welcome to the first part of the problem-solving session for Chapter 13. Let's begin with the first question. Here, we're told to use the center-to-center distance between the Earth and the Moon, which is 3.84 e to the 8 meters, to determine the force of gravity between the Earth and the Moon. And specifically, we're told to determine the force that the Earth exerts on the Moon and to compare this force to that which the Moon exerts on the Earth. Well, let's see. We need to start. Let's first extend our page here. We need to start with Newton's law of gravitation, which says that the force of gravity between the Earth and the Moon equals big G, the gravitational constant, universal, times the mass of the Earth, that's our m1, times the mass of the Moon, that's our m2, divided by the distance that separates the two. And when they say center to center, we consider all of the mass of the Earth to be concentrated at its center, all of the mass of the Moon to be concentrated at its center, and so the distance between these two concentrations of masses is what was given to us as the center-to-center distance. Well, let's see. G is 6.67 e to the minus 11. Mass of the Earth, 5.98 e to the 24 kilograms. Mass of the Moon, 7.35 e to the 22 kilograms. Oops. Divide that by their distance of separation squared, center to center, 3.84 e to the 8 meters, square that, and we get 1.99 e to the 20 newtons. Now, this is the force of gravity that the Earth exerts on the Moon. What would be the force of gravity that the Moon exerts on the Earth? Newton's third law guarantees that it will be the same magnitude. And in fact, that's quite obvious here, because if we switch places between mass of Earth and mass of Moon, that is not going to change the product of the two masses. And so the magnitude will be the same. Of course, the direction will be reversed. The Moon pulls on the Earth along this direction. The Earth pulls on the Moon along this direction. And so you can see the directions are opposite, but the magnitude of the pull is the same. Why is it then that the Moon goes around the Earth? Well, that is because the Moon, being less massive, 100 times less massive, experiences the greater acceleration. And not only that, but when we get to Chapter 9, we'll learn about something called the center of mass. And in fact, let me just get something read here. The center of mass of the system of Earth and Moon happens to be a point which is located within the Earth itself. And so the Earth tries to go around that point, but of course, since it's inside itself, it can't. The Moon, in fact, goes around that point. And so when we see the Moon in orbit about the Earth, the Moon is really orbiting about this point, which we call the center of mass, or CM. More to come in Chapter 9. Next question. Here, we are told that the Hubble Space Telescope has a mass of 11,600 kilograms, and we'd like to know what it weighs in the following two circumstances. Well, the first part says it wants the weight, which we also know is the force of gravity, when Hubble is on the surface of the Earth. Well, in this case, we know we have Hubble's mass times the gravitational acceleration on the surface of the Earth, which of course is 9.8 meters per second squared. When we substitute 11,600 kilograms for the mass, and we multiply by 9.8 meters per second squared, we get the weight of Hubble as, and here I won't round so that we can look at the full number, 113,680 newtons. Of course, if we had to round this to 3 significant digit, it would be 114,000 newtons. Well, what about when Hubble is at its orbital altitude? Well, here we're told the orbital altitude is 5.98 e to the 5 meters. Now keep in mind that what this represents, if this should be the Earth right here with its radius r sub e, Hubble is placed someplace out here where the altitude h is from the surface of the Earth to the location of Hubble. However, the distance that separates the Earth, the concentration of mass of the Earth, which is at the center, and Hubble is little r, which equals the radius of the Earth plus its orbital altitude. So we have to take that into account in this calculation. So the force of gravity here is going to be the mass of Hubble times, let's see, this we need to find the effective G. The little g effective. Of course, big G is a constant, universal constant, so that never changes in value. And because Hubble goes around the Earth, we take the other mass to be the mass of the Earth. But instead of dividing it by just the radius of the Earth, we have to divide by the radius of the Earth plus its orbital altitude. And so this right here becomes an effective G, which is going to be smaller than 9.8. You see, because coming back to here, let's recall how we got G of 9.8. G of 9.8 is the gravitational constant times the mass of the Earth divided by the radius of the Earth squared. Because in this case here, we're assuming, if this is the radius of the Earth, that Hubble sits on the surface of the Earth, and so h is 0. This is equal to 9.8. That's how we came up with that number. As soon as we put Hubble at a greater height above the center of the Earth, in other words, the radius of the Earth plus altitude, we now have a different value to calculate. So let's see, 11,600 kilograms is the mass of Hubble times 6.67 e to the minus 11 times 5.98 e to the 24 kilograms, 20 kilograms, okay, divided by, now we have to, let's go ahead and just close up our bracket. Divide by 6.37 e to the 6 meters plus 5.98 e to the 5 meters, the whole thing squared. See, we got to square the whole thing now. And this gives us a weight which is reduced because, of course, Hubble is further away, 95,295 newtons, which you can see is smaller than 113,680 newtons. Next question. Here we're told the planet Saturn has a radius 6.03 e to the 7 meters, a mass of 5.69 e to the 26 kilograms. First question, what is the acceleration of gravity on the surface of the planet Mars? Well, this is what we're being asked to determine. The G value on the surface of, sorry, not Mars, Saturn, on the planet Saturn. Okay, well, just as we saw that we had calculated the G of the Earth, we have to take big G, gravitational constant, always has the same value anywhere in the universe, times this time the mass of Saturn, not the mass of the Earth, divided by this time the radius of Saturn squared, not the radius of the Earth squared. You see, because the gravitational acceleration will be unique to every planetary body depending on what their mass is and what their radius is. Well, when we substitute our numbers, which I think I'm going to run out of room here, but I'll go ahead and just try. 6.67 e to the minus 11, 5.69 e to the 26. Let's go ahead and put our unit. Units are always important. Divided by 6.03 e to the 7 and square that. That gives us a G, acceleration of gravity, that is 10.43 meters per second squared. So you can see it's a little bit bigger than that of the Earth. So you might say, well, look at the radius of the planet Saturn. It's 10 times bigger than that of the Earth. Yes, but its mass is 100 times bigger. So effectively what happens is, because we have a numerator that's 100 times more and a denominator that's 10 times more, of course we're squaring the denominator, which means 10 squared is 100. Effectively, it doesn't increase the value of G that much more than that of the Earth. Anyway, in part B it says, if a man weighs 588 newtons on the Earth, okay, that is on the Earth, what would he weigh on the planet Saturn? Well, when they're giving us his weight on the Earth, they're giving us his mass times the acceleration of gravity on the Earth. In order to determine what he weighs on the planet Saturn, we have to take his mass. See, this is on Saturn, this is on the Earth. We have to take his mass and multiply it by the G of Saturn. So how do we get his mass from here? Well, we know mg equals 588. So m must equal 588 newtons divided by 9.8 meters per second squared. That gives us a mass of 60 kilograms. Now we can use this mass, 60 kilograms, with the result that we obtained earlier, 10.43 meters per second squared, and now we get his weight on the planet Saturn, 625.8 newtons. Next question. Using the center-to-center distance between the Earth and the Moon, which we saw earlier, 3.84 e to the 8, and again, that's from all the mass of the Earth concentrated at its center, all the mass of the Moon concentrated at its center. Determine the Moon's orbital period. Okay, well, let's see. According to what we have, and of course also due to Kepler's third law, which we saw at the end of our lecture, T, the orbital period, is given by 2 pi r to the 3/2, the distance of separation to the 3/2, divided by g times, and now it's a matter of determining, do I put the mass of the Moon or do I put the mass of the Earth? So my question to you is, which one goes around which? Is it the Moon that goes around the Earth or the Earth that goes around the Moon? I'll give you a second to think about that. Oh, good. You said the moon goes around the earth. Therefore, it's the mass of the earth that gets placed in the equation. It is always the mass of the object about which something goes around that we put in the denominator. And this does come from somewhere, and I'll remind you from where in a minute as soon as we're done with this calculation. And I'm going to scoot over here because there's a lot of writing here we have. 2 pi, center to center distance 3.84 e to the 8 meters. Take that to the 3/2, and be careful when you enter this in your calculator because you're going to have to use a lot of parentheses. 6.67 e to the minus 11 times 5.98 e to the 24. Close our bracket to the 1/2. So very carefully enter your numbers in your calculator, and you should get something which looks like 2,367,354 seconds. What is that? Well, let's go ahead and convert using the fact that there are 86,400 seconds in a day. If we divide this number by the number of seconds in a day, we get 27.4 days. That, in fact, is what is known as the sidereal, or the true orbital period of the moon about the Earth. But of course, days is not an SI unit, so in the SI system, the answer would be given in seconds. Now, as I promised you, where did this expression come from? Well, a little reminder. We start with Newton's second law. Force equals M, and in this case, A sub C, because the moon's going around the Earth. This is the mass of the moon. Well, the force of gravity is the force that the moon feels. And that's G, mass of the Earth, mass of the moon, divided by their distance of separation squared. If we now rewrite mass of moon times V squared over R for A sub C, notice that the mass of the moon cancels. This radius cancels one of those, and that gives us V equals the square root of G, mass of the Earth, divided by R. So I hear you say, how do we get T out of that? Well, here's how we get it. We know T is equal to 2 pi R, the circumference, divided by V. If we substitute this V into our expression, we get 2 pi R divided by square root of G, mass of the Earth, divided by R, under the square root sign. But we can simplify this and bring this R, that is to the 1/2, up to the numerator, so we have R to the 1 plus R to the 1/2 becomes 2 pi R to the 3/2 divided by the square root of big G times the mass of the Earth. That's how we came up with that expression. Next question. Use the fact that the Earth completes one revolution around the Sun in 1 year, which gives us this many seconds, and that the average distance between the Earth and the Sun is 1.496 e to the 11. Determine the mass of the Sun. We want the mass of the Sun. Well, how do we approach this? Let's first write down what they gave us. They tell us that the time for the Earth to go around the Sun is 3.156 e to the 7 seconds. See, this time it's the Earth that's going around the Sun. The problem we just saw earlier was the moon going around the Earth. Okay? So they give us the orbital period and they tell us the distance of separation, 1.496 e to the 11 meters. How can we get the mass of the sun? Well, if you recall, our expression T has 2 pi r to the 3 halves, we know what r is, divided by the square root of big G times, and remember here, what's going around what? Is it the Earth going around the sun or the sun going around the Earth? Well, of course it's the Earth going around the sun. So in this expression, it's the mass of the sun, which is going to be in the denominator, because this will be the term that from the little derivation we did earlier does not get canceled out. All right, so we need to work with this expression to solve for the mass of the sun. We use a little bit of algebra. Let's square both sides because after all, we want to get rid of this square root. T squared equals 4 times pi squared times r cubed divided by big G, mass of the sun. Well, now we just multiply both sides by mass of sun, divide both sides by T squared. In other words, get M here, T squared down here. MS equals 4 pi squared r to the 3 halves divided by G times T squared. Plug in our numbers. 4 pi squared r is equal to 1.496 e to the 11 meters. Take that, cube it. Oops, that shouldn't be, mistake right here. That should be just cubed, right? Because remember we had we eliminated once we squared. So that's a little error there. Please make that correction in your notes. 4 pi squared times r cubed divided by 6.67 e to the minus 11 times 3.156 e to the 7 seconds, and that gets squared. 1.99 e to the 30 kilograms, and if we check the table in the book to see front cover, back cover, what the mass of the sun is, in fact, it is correct. Next problem. Here we're told that a geosynchronous satellite is a satellite whose orbit above the equator of the Earth has the same rate of rotation as the Earth. So in other words, if it takes the Earth 86,400 seconds to rotate about its axis, that's how long it takes for the satellite to go around the Earth, so that the satellite is always at the same fixed point about the Earth. So for example, if this is the Earth right here and here is the satellite, we want that as the Earth goes around its axis, the satellite always rotates so that it's always, if this is Florida right here, here's Florida, and this is our satellite dish, that our satellite dish can always find the satellite. So T for a geosynchronous satellite is 86,400 seconds. The question is, at what altitude should we place this satellite so that it ends up with a T of this value? Well, here again, the same familiar expression, except that we have to be careful once again that we're dealing with an R, which is the radius of the Earth plus the altitude of the satellite above the surface. So how about this? Before we even get H, let's try solving for R and then manipulate R so that we subtract out the radius of the Earth. Familiar expression T equals 2 pi r to the 3 halves, and here we're talking about this little r, divided by Well, let's see. If the satellite goes about the Earth, it's g times the mass of the Earth. Square both sides, as we saw earlier, and we end up with t squared equals 4 pi squared r to the third divided by g, mass of the Earth. We're solving for r, so r cubed will equal t squared times g times mass of the Earth divided by 4 pi squared. Take the 1/3 of both sides, the cube root, that is, of both sides. We're going to get then r equals t squared. Okay, let's go ahead and just plug in those numbers. We might as well. 1/3. And let's start way over here, and let's hope we have enough space here. T is 86,400 seconds. That's going to get squared. G, 6.67 e to the minus 11. ME, mass of the Earth, 5.98 e to the 24 kilograms, just enough room, divided by 4 pi squared. Now, here's something we do at this point. We recognize that r is equal to re, the radius of the Earth squared, plus h. So how about we rewrite this expression and subtract re from this number? So in other words, take this number right here, whatever we get, minus r sub e, and that will give us h. And when we do so, because I didn't get a number here first, but when we do so, let me just write h now on the left-hand side, we get 35,880 e to the 3 meters. And of course, e to the 3 is kilometers. Now, why did I write it this way? Because I wanted you to see what this result is in terms of miles, because that may be more meaningful to you. All geosynchronous satellites in orbit about the Earth at the equator orbit at 22,300 miles above the surface of the Earth. That's why I wrote it this way. Otherwise, you would write, and in 3 significant digits, you would write 3.59, right? Because this 8 would become a 9. E to the, let's see, e to the 3 plus e to the 4 is e to the 7 meters. Okay, next question. During the manned Apollo missions, whenever 2 astronauts were on the surface of the moon, a third one orbited above the moon. In the CSM, Command Service Module, assume that the orbit had a value h, again this is altitude, 1 e to the 5 meters above the surface. The radius of the moon is 1.74 e to the 6 meters. The mass of the moon is 7.35 e to the 22 kilograms. And answer the following. First question, what was the acceleration of the astronaut that didn't get to come down to the moon? The one that was in the Command Service Module, the CSM. Well, he's at the altitude. So to get his acceleration, and of course it'll be centripetal, and you can think of it as another way that you can think of it is as the effective g above the moon, okay, the surface of the moon. And to get the g, and this I'm calling it effective because it's not on the surface of the moon, we get capital G, big G, that's a universal constant, times the mass of the moon, divided by, here we got to be careful because we are going to have to use a little r, which is the sum of h plus rm. And when we sum these, I get 1.84 e to the 6 meters. So rather than write it separately, I'm going to write little r squared. We plug in our numbers and we get a sub c equals 2. And rather than write the whole thing out, well, let's see, we could do that. 6.67 e to the minus 11, 7.35 e to the 22 kilograms divided by 1.84 e to the 6 meters, and that's got to be squared. That gives us a value of 1.45 meters per second squared. All right, what was the orbital speed of this CSM? Here, if you recall, V is equal to capital G, universal constant, this time mass of the moon, because the CSM is going in orbit about the moon, divided by R. And if you can't remember how we came up with this expression, let me once again remind you, big G, mass of the moon, mass of the command module, see the CSM, divided by R squared equals mass of command module, V squared over R. And of course, masses cancel here. One of these R's cancels there, and that's how we get V. Well, let's plug in our numbers. Square root of 6.67 e to the minus 11, 7.35 e to the 22 kilograms divided by 1.84 e to the 6 meters. And we don't square that because it's just r. That gives us an orbital speed of 1,632 meters per second. Question: what if we would have used the fact that a sub c equals v squared over r, and we would have solved for v as the square root of a sub c times r, using 1.45 for a sub c and using 1.84 e to the 6 meters for r, oops, not squared, sorry, for r, and the square root. Would we have gotten the same number? Check it out. The answer should be yes, because of course the expression that we got earlier was derived from that. Last, what was the orbital period of the CSM? How long did it take for it to go around? Well, here we can use this big expression right here with G times, what M are we going to put here? What goes around what? Oh, CSM goes around the moon, therefore it's the mass of the moon. But we can also use 2 pi r over v. Since we have already obtained our v, this is our v right here, we can make this expression a little easier to work with. 2 pi, the r is 1.84, v is 1.632, and we get an orbital period of 7,083 seconds. That's our t. And again, if we do a quick conversion, 1.97 hours. That's how long it took the CSM to orbit about the moon. Okay, last question. The spring and fall equinoxes are 2 points on the Earth's orbit about the sun, which are 180 degrees apart. When the Earth travels from the spring equinox to the fall equinox, it takes 185.4 days. However, when it travels from fall to spring, it takes less. Why is it that it's taking less or longer or shorter time to cover the same distance. All right, well, let's go ahead and put the sun here so we can go ahead and get a visual of that. And because the Earth's orbit is elliptical, the sun is at one focus and there's another focus here. And the ellipse, of course, I am going to exaggerate the ellipse and really make it oblate. When the Earth is here, it is furthest away from the sun and it travels the slowest. Well, when is that? The month, believe it or not, when the Earth is at aphelion, let's write down the point, aphelion, happens to be July. When the Earth gets here, and what they're saying, the same distance is from here to here is the same distance as from here to here. The distance hasn't changed. However, when the Earth is at perihelion, let's write this down, the Earth is the fastest in its journey. Okay, so what is happening here, and that's the month of January. So what is happening here is that the Earth is speeding up on its journey from July to January. Well, what month is between July and January? It must be September. So September is in between July and January. Well, when the Earth is traveling from aphelion to perihelion, it's speeding up. It's speeding up because it was at its slowest, and as it approaches the sun, it begins to gain speed. On the other hand, when the Earth is traveling from perihelion to aphelion, it is slowing down. Why? Because it was at its fastest. Here would be March, the Earth in March, and as it moves further, it's slowing down. So the question is, if it takes 185.4 days from March to September, okay, here's March to September. See here, the Earth is slowing down, and it has to pass the slowest point to get to September. It takes 185.4 days, except that when it travels from fall to spring, it only takes 179.8 days. Why? Because it was speeding up at its fastest and then slows down here. So it has to do with the fact that the Earth is moving faster when it's traveling. Let's go ahead and go this way. When it's traveling from here to here, and when it's traveling from here to here, it is traveling slower because it reaches the slowest point here, whereas here it reaches the fastest point here. Well, that concludes the end of the first part and only part of Chapter 13, Lecture Problems. Until next time.